Welcome to Physics Clinic at the Red Rose Academy. Today's topic is magnetic field on the axis of a circular current loop. Imagine winding a wire into a circle, now pass current, instantly it becomes an electromagnet. But how strong is the magnetic field at different points? Today we will derive the famous equations. Okay, I must say the real life applications, for example, loudspeakers, MRIs, electromagnets, particle accelerators, all depends on current loops only. Okay. So I will introduce right now. In this section, you are going to evaluate the magnetic field due to a current coil along its axis. The evolution entails summing up the effect of infinitesimal current elements. Okay. So you are taking a small element of current here. Okay. So in this, once again, you are taking a small element of current in this. Okay. And then here, I mean, this is a total current loop. Inside the current loop, there is a small element. You are taking a small element of current loop. So total loop length will be L. So you are taking since you are taking a small infinitesimally small length, so it is element dl. And then current I is passing through this particular thing. So like current is passing through this. Okay, in the anti-clockwise direction like this. Okay, so here suppose if you want to find the current IDL, so and then you can sum up like, so here also IDL, here also IDL, so you can sum up, take or integration overall, so it will be the total magnetic field. Okay, so we'll see how to derive the magnetic field now. Okay, so this is an axis. Okay, it gets y and z axis. The current loop is taken in, the loop is placed in the yz plane like this. Okay, with its center at the origin and has radius r. The x-axis is the axis of the loop. This x-axis is the axis of the loop. Okay, like this you have taken. And we wish to calculate the magnetic field at the point P on the axis. Let x be the coordinate distance, okay, of P from the center O of the loop. So considering conducting element dl of the loop, this is shown in the figure. Okay, so the magnetic field dB is now calculated. Okay, this is dB. You can resolve the magnetic field into two components, dB at P, because here the current is flowing through this. Okay, so how the magnetic field will be? The magnetic field will be emerging out like this. So this is the magnetic field. Like this, the magnetic field emerging out of the loop. Okay, so lines of forces. So it is dB. At the point P, we are calculating. So it is resolved into two components, dBx, and that is the horizontal component and the vertical component. Okay, so consider a current element. Okay, so what is dB now? Mu naught by 4 pi using Biot-Savart law. Mu naught by 4 pi, 2 pi, I mean, IDL dot cross R. This is the cross product, okay? IDL cross R by R cube. Okay, so this is the Biot-Savart law. We are going to apply this law here. What is R from this picture? From this picture, you can able to predict this R by means of this right angle triangle. By applying the Pythagorean theorem, R square is equal to sum of the squares of the other two sides. So R square plus X square, right? So then you can apply this in the place of R cube, and also it will be I dl cross R product means dl into R into sine theta, it will come. Okay, then if you substitute for theta, okay, for example, any element of the loop will be perpendicular to the displacement vector. Okay, right. So all the displacement vector, any element is perpendicular to the loop. Okay, then from the element to the axial point. Okay. So for example, the element DL in the figure 4.9 is in the YZ plane, whereas the displacement vector R from DL to the axial point is in the XY plane. So YZ plane and XY plane are perpendicular. See here, let me explain again. See, as I've already told you, your book is actually a summary, a bit summary. Okay. The points are given. You have to understand what is it. So this is along the circular loop is along YZ plane. This R is along XY plane. These two planes are perpendicular to each other. This plane is like, this is one plane and this is another plane. So these two planes are perpendicular together. So for each element of DL you have taken, for each element of DL, okay, this axial distance is also perpendicular to it. Okay, if you are taking axial distance, it is perpendicular. That's what they have explained here. So perpendicular means what is the angle theta? The angle theta is sine 90. So sine 90 is equal to 1. Then you can make it like dB equal to I dl r sine 90 by r cube. So I dl r only there, one r gets cancelled, so r square. So mu naught by 4 pi will be there. Mu naught by 4 pi. Mu naught by 4 pi I dl by r square. Then r square can be replaced by the formula, that is Pythagorean formula, x square plus r square. Okay, so this is what here explained. I hope it is clear for you now. So if you want, you can take a screenshot, then it is easy for you. Then we'll see now the two components. Okay, how the two components we are going to see. Okay, so now dBx is the x component and perpendicular to x axis, right? See, okay, so it has an x component dBx and a component perpendicular to x axis, perpendicular component. Two components are there. When the components perpendicular to the axis are summed over, they cancel out and we obtain a null result. Okay, so dB vertical component due to DL is cancelled by the contribution due to the diametrically opposite DL element. So we are taking only x component. So how they are trying to say here, if you are taking this dB into two component, okay, if the DL element, suppose if you are taking DL element from here, so, and then from here, the dB element will be like this, dB will be like this, okay. So dB perpendicular, but dBx will be added up, okay. If you take the DL element here, then dB will be here and dBx will be here and dB perpendicular will be here. So listen carefully, children. It is very, very important. Then you may not know how it cancels together. So these two components, if you sum up, it will be plus, it will be minus. So it is cancelling. And here dBx is both plus. So it is summed up. So it's listen to this. And you'll be taking what is dBx cos. dBx will be dB cos theta. You know that horizontal component is the cos theta component. Okay. And then you are going to get cos theta from this. This will be capital R square plus x square. Then if you take this as 90 degree, okay, and this is theta means this will be theta. So what is the cos theta component? R by r square plus x square, right? So that is cos theta component. Okay, it is root of. So r is the adjacent side. This is hypotenuse. Okay, if this is theta and this one is theta. So cos theta is equal to, if you want to find dBx component, dB cos theta. And then for this cos theta, we can take it from here. Then this adjacent by hypotenuse will be Okay, so r by root of r square plus x square. So you are going to substitute in it. And then for dB, already we found from this. This is dB. Okay, so what is dBx now? Mu naught by 4 pi I dl is there already. And already it is x square plus, listen to this, derivation, very important for you. So r square plus x square, here it is, okay? And here for cos theta, you have to substitute r x square plus r square, the whole power 1 by 2. So what it will be, this will be whole power 1 and 1 by 2, then it becomes 3 by 2. Is it clear? So from this, this derivation is. So write down all the intermediate terms. So below this dbx, you have to write this. Then this step, okay? From this and this. So you just write all the steps. Then what is this b? B is right now you can able to understand. So if you take the summation over all dl, then overall length, if you take the circumference will be the overall length. So 2 pi r, okay? So magnetic field is B overall. Okay, not dB, it will be B. So it is along the x-axis only we are taking. So bx I cap it will be. So bx is this one. Bx in this, how we are going to write, instead of this dl, listen to this carefully. Dbx is now turned to bx. How it will be bx? Mu naught I, this instead of this dl, you are going to substitute for the whole circumference, whole L, 2 pi r into r by 4 pi into x square plus r square whole power 3 by 2. Okay. Then this 2 pi and 4 pi gets cancelled. Then you'll be having bx I cap is equal to mu naught I r square it is. R square by 2 into x square plus r square, the whole power 3 by 2 into I cap. Clear? This is what given here. We'll see some cases. Suppose if you want to find the magnetic field at the center of the loop, you need to make this x as 0, right? If you place this x as 0, then this magnetic field you can able to find at the center. Okay, so put x is equal to 0. Then what it will be? If you put x equal to 0, mu naught I r square by 2 r square the whole power 3 by 2. Okay, so r cube will be there. In this r cube, 1 r square gets cancelled. So 1 r will be there. So mu naught I by 2 r into I cap. Clear? So this is what? It is the magnetic field due to a circular wire at the center. Okay. So this is the magnetic field due to the loop of a wire. So circular wire which form closed loops and are shown in the figure 4.10. Okay, can you able to understand this? So the direction of the magnetic field is given by another right hand thumb rule here. Here you have to explain like this. The curl of the finger. Okay, listen to me. The curl of the finger is the it represents the current loop where the current is passing through it. This thumb represents what? It is the direction of the magnetic field. If the curl of the finger is like this, if the current is flowing through this, like this, okay, anti-clockwise direction, then the magnetic field will be flowing upwards. If the current is in clockwise direction, the magnetic field will be flowing downwards. Like that, the direction switched. Okay. So here for a loop, the curl of the finger represents the current loop where the current is passing through, and the thumb represents the magnetic field direction. For a straight long conductor, by applying the Biot-Savart law, we saw here that long conductor, according to Biot-Savart law, if the current is passing through the straight conductor, the thumb represents the current direction or the conductor, and the curl of the finger represents the magnetic field. So here it is ulta. Okay, so keep in your mind the directions and all. So it is very, very important. Okay, You are taking the radius is R, current as I, okay, the point P from the center. So every current element contributes dB and everything. And then you are applying the Biot-Savart law. Okay, due to symmetry, horizontal components, sorry, vertical components cancel. Okay, so horizontal components only exist. Okay, then the derivations now and special cases also, Okay, so from here, very if it is, so it is inversely proportional to R. Okay, it is inversely proportional to R. If the circular loop is very big, it is very far away, then the field decreases rapidly. Okay, so you can understand the magnetic field depends on the current I, directly proportional. Can you write, students, like a memory trick? Memory trick. You can write like this. Okay, current. Okay, it is directly proportional. That means field increases. If the current increases, then the field also increases. So field depends on. Field depends on current. Okay, directly proportional. And radius squared, if you take this is the magnetic field. Okay, radius squared, right? Radius squared. It is also directly proportional. Then distance cubed. Distance cubed. So this total distance, x square plus r square. So this radius is different from x square plus r square. The distance cubed, okay? Then the field decreases. Okay? Can you able to understand this? Field depends on all these three parameters. Okay? So center formula also, Okay? And then suppose, for example, if I'm giving you the loop radius, 20 centimeter, okay? Then current 5 ampere, okay? What is the field at the center? You can easily solve it, right? You can substitute 4 pi into 10 to the power of 7 for mu naught, okay? And then do calculate everything. Then you can find out the field at the center, okay? So how can you find out? B naught is equal to 4 pi times 4 pi times 10 power minus 7 times 5 ampere by 2 times radius is in centimeter, you need to convert into meter. Okay. See here, students always forget to put what are the common mistakes they will do. They put r square or r plus x square like that they will put. Okay, so you need not worry about all these things. Suppose for at the center, if you're asked at the center, this is the answer. Okay, generally for the magnetic field to the whole loop, if you are asked to find the whole loop at some point P, at some distance, okay, if the distance is given, some field at center, suppose if the distance is at 2 meter, like distance 2 meter, then you have to use this formula. So if you use this formula, the students has committed some mistakes, like you have to represent B as a vector. So vector sign is very important. What is the mistakes? Instead of writing r square here, x square plus r square the whole power 3 by 2, the students may wrote r square, or simply it is r square plus x square like that. So do remember it is whole power 3 by 2. So you have to solve all these things. Mu naught is 4 pi into 10 to the power of 7, and I is 5 ampere, and R is 20 centimeters, so 10 power minus 2 whole square. Then 2 into x will be 2 meter. Then this R will be 0.2 the whole square. It is 2 square. Then whole power 3 by 2 will be there. So don't forget to substitute everything and find out. Okay. So every circular loop behaves like a tiny magnet. This concept becomes the foundation of solenoids and electromagnets also. We'll see further. Okay. So then you can go through this example and let me know your doubts if there is any. Okay. It's very important. So it shows about the direction only. See here, a straight wire carrying a current of 12 ampere is bent into a semicircular arc of radius 2 centimeter. Okay. 2 centimeter. Consider the magnetic field B at the center of the arc. So what is the magnetic field due to the straight segments? And so you are asked to find the magnetic field at the straight segments. Okay. And next one, okay. What is the magnetic field due to the straight segments? In what way the contribution of B from the semicircle differs from that of the circular loop, and in what way does it resemble? That is another question. What would your answer be different if the wire were bent into a semicircular arc of the same radius, but in the opposite way like this? So these three questions has to be solved. So for the first question, DL and RF for each element at the of the straight segments are parallel, right? These are parallel, straight segments are. So parallel sign 0, right? Parallel means it will be 0. DL cross R product will be 0. Cross product will be. So straight segments do not contribute to B. So this is the very great fact you have to understand from this. What is the second question? For all segments of the circular semicircular arc, DL cross R are all parallel. For all segments, it will be like that. If you take here, it will be. Okay. So it is parallel, and also all such contributions add up in magnitude. Okay. Hence, the direction of B for a semicircular arc is given by the right hand rule. Okay. For a right hand rule, if you take, then the thumb represents the magnetic field direction. Okay. The curl of the finger represents the coil. Or the current loop, like that we can take. Semicircular current loop. If you are taking this is the current loop. Okay. Then the magnetic field, how the magnetic field will be, if the current is passing through this, okay, clockwise means the magnetic field will be like it moves inwards, okay, like this. Okay. So that's what here it is given by applying the right hand rule, and magnitude is half that of the circular loop also, because it is semicircular, it is half that of the circular loop. So the magnetic field is given in Tesla here. Using the formula, you can substitute all the values in that. The formula remains 1.9 times 10 power minus 4 Tesla. You can substitute everything here. Okay, B is equal to mu naught by 4 pi. Okay, so everything you have to find out. So it will be 10 power 7. And then what is that current? Current is 12 ampere. Okay. And it is a semicircular arc of radius 2 centimeter, right? So, and then you have to substitute everything. And then at the center only you're going to do, then you can use 2R formula. This formula, mu naught I by 2R. By 2 into R is 2 centimeters. So 2 into 10 per minus 2 meter. Okay. Substitute everything. Then you'll be having 10 per 7. Here it will be 4 times 10 per minus 7 minus 2. Okay. So what is 12 by 4? It will be around 3, right? Then divided by 2 also. So 1.5 something it is coming. Okay. So half that of the circular loop, right? And also normal to the plane of the paper going into it. That also, it is normal to the paper. Like, sorry, going into it like this. It is not going out, it is going into it. Okay. So you'll be getting the answer. Do calculate like this. It is going into it. Here also like it is going into it. Like, okay. So the magnitude will be same, right? But opposite in direction. Then the same way you can calculate all the stuffs here. Sorry, it is 10 per minus 7 you have to put. Okay. So same way you are going to find out all the things. Okay. The answer will be 2 pi into 10 to the power of minus 4. So you have to substitute for pi also. Okay, then finally you'll be receiving the answer. So this is the formula. Just keep in your mind. Okay, because here number of turns also given, so you have to multiply the number of turns. Since it is at the center of the coil, you need to use this formula. Number of turns are given, so that n is added here. Okay, so mu naught, sorry, not mu naught by 4 pi, it is only mu naught. Okay, so what is the answer here? B naught is equal to 4 pi into 10 to the power of minus 7 times I will be 12 ampere, then 2 into 10 per minus 2, since it is given in centimeter. So you have to find out all these things. 4 and 4 gets cancelled. Then pi will be 3.14 times 12 into 10 per minus 7 plus 2. Okay. So you can find out what is 3.14 into 12. What is 3.14 into 12? Calculate now, students. 3.14 into 12. Exactly it is. And divided by 2 also we have to do. Because it is half semicircle. So it will be whole divided by 2. Okay. And then what it will be now? 37.68 into 10 to the power of minus 5 divided by 2. It will give 18.84 times 10 power minus 5. Or we can write 19 into 10 power minus 5 Tesla, or we can write this and all B vector, or we can write 1.9 into 10 to the power of minus 4 Tesla. Clear? So this is the formula you have to keep in your mind. At the center, magnetic field of a current loop at the center, since it is a half semicircle, you can divide it by 2. Okay, so like this you have to find out. Then it says Ampere circuital law. So this we can see in derivation. So suppose I ask you to calculate the magnetic field around an infinitely long wire, you can use Biot-Savart law forever. Can we do it in one line? Yes, that's why Ampere developed his famous law. Say, for example, this is the wire, the same wire. This is the wire. Long, what is that? It is the infinitely long wire. It is going on. So he cut one portion. So one portion of the wire like ring. See, like this, like a ring it is. Okay. So it has the surface or boundary. You can think it of. It has the surface or boundary. Like this, we can cut like all boundaries. Like that, we can cut all the whole portions, right? So, since it's an infinitely long wire, okay, so magnetic fields form closed loops, Okay. Then instead of calculating every tiny contribution, we integrate around a closed path. Okay, so we'll see now. So it is like a Gaussian surface. You have to analyze, you have to keep an analogy with the Gaussian surface. It is Ampere circuital law is the Ampere in surface. You have to consider this boundary as an Ampere in surface. Okay, consider one such element of length dl here. Okay, it is the length element dl. Okay. So you have taken the wire in a three-dimensional way. If this is a wire, you have taken the wire and cut a small portion of a wire. The length, this is total length means you have cut a small wire, small portion of a length. So that is DL. That DL looks like this ring. Okay. So if you cut the small portion of the wire, it looks like this ring. Okay. So it has the boundary like this blue shade, right? Given here, it has the boundary. So it is the length dl. Okay. So take the value of the tangential component of the magnetic field. So where the magnetic field will be around. So it is like a tangential component. Okay, so the element and multiply it by the length of that element. Okay, so B tangent dot dl, like what we did for Gauss law, E dot dl, right? The same we are going to do here. Okay, then all such products are added together, and here we are going to use what, the line integral. Okay, so we integrate around a closed path. Okay, the line integral of a magnetic field around any closed path. Okay, so it is equal to mu naught times I. Mu naught times this I is the enclosed current. Okay, so this is called the Ampere circuital law. This is very important. Ampere's law. Okay, it states that the line integral of magnetic field around any closed paths equals mu naught times the enclosed current. Okay, so for derivation, we had to choose circular Amperian loop. We saw, right? So we had to choose that. And B is constant. The magnetic field is constant in it. The integral becomes, how it becomes? B, the dl will be now, so if you take the whole element like the total enclosed surface, B and dl will be 2 pi r, right? Since the loop's circumference will be. And then it will be mu naught I. What is the magnetic field now? Mu naught I by I enclosed here. Hmm? 2 pi r. This is the derivation. That's it. Okay. So it is for a straight, infinitely long wire. Okay. So it is more enclosed current, more magnetic field. No enclosed current means integral becomes zero. Okay. If it is open, the integral becomes zero. So many applications are here. Solenoid, toroid, infinite wire, etc. So it works only when symmetry exists. This is also very important. Okay, so this is all about the Ampere's circuital law. It implies that here also you can understand every point on the circle of radius. It implies that the field at every point on the circle of radius, right? It possesses cylindrical symmetry. I told you, no. It's very important. The symmetry is very important. Ampere's law works on only symmetry. When symmetry exists, it will work. So cylindrical symmetry, we know that, right? The Gaussian surface also like that. Okay. So the field that normally can depend on three coordinates depends only on one, or right. Whenever there is symmetry, the solution simplify. Okay. So always we have to use symmetry. Then the field direction at any point on the circle is tangential to it, that we know. Thus, the lines of constant magnitude of magnetic field form concentric circles. So, like this, we can say it forms a concentric circle. Suppose if this is a current wire, okay, like so. In the next one, we are going to see like that. See here, this is a wire. Okay, it forms a concentric circle, right? So, if you take the section, so this is Ampere loop. Okay, if you take the section of the wire, and then you can consider the Ampere loop inside the wire also, or outside the wire also. And then if you see, the magnetic field forms a concentric circles like. Okay, this is very important point you have to understand. These lines called the magnetic field lines form closed loops. This is unlike the electrostatic field, which originate from positive. Electrostatic field, it originates from positive to negative. But this is like a concentric circles. Okay. The expression for the magnetic field of a straight wire provides the theoretical justification to avoid state experiments. These are all cancelled for your it is not in your syllabus, but it will be more important for your NEET and JEE.